Are you using KBB or Athens?
Yeah.
Or price to house using realestate.com or whatever. What is that other one? Is that something with a Z? Okay, regardless, there are tons of these sites or tons of these tools where you plug in some information and you get back an estimated price or something, right? Okay. That's all regression based. You're basically just accessing a model, right? There's no, let's say we're dealing with mileage in cars. You're not going to plug in minus 10,000 miles because there are no cars with minus 10,000 miles. Nor are you going to plug in a car with 1,000,000 miles if no cars have that many miles in their database. You'll simply not get a reliable answer. And they'll tell you you won't get a reliable answer. So you use, 10,000 miles up to 250,000 miles, something like that. And within that range, you're good to go. So that's why. It's really just a question of reliability. How much can you trust your model? And when answering the question, how much can you trust the model, you also have to ask, how much can the model explain? So,
I guess it doesn't look like we got a lot of value from our observing the data and saying, this is about where it is, to going, this is exactly where it is. There was...
oh, well, I can tell you what you got. What you got was the data speaking to you directly rather than somebody just drawing up a line subjectively. You got something else too. You got a way to formally test whether or not the data actually does have a trend, or you're just seeing pictures that aren't there, seeing patterns that aren't there, which we as humans are remarkably good at. So there are a couple of advantages to it. Further, we'll expand this. Instead of doing it in 2 dimensions, we're going to be doing it in 10 dimensions. Really hard to visualize 10 dimensions, whereas this has no trouble.
Okay.
So we need to ask ourselves, what can we do to answer the question, how much of the variation in y are we explaining? So the first thing to note is the following. If in fact your data is not really related to x at all, what is the best estimator for y?
Constant.
Beta hash. Beta not hash.
Well, okay, sort of. You think this is the best estimator for y? Y is what you read off over here, because we have 0 here. Okay, so what would we put up here?
Like.
Yes, but,
Range.
well, but we can't use the range, we just need a single number. What's the best single number to represent
bar.
this? Y
Y bar.
bar. So, if y bar is the best estimator, you have a flat line. If you have a flat line, what's the value of the slope? 0. Now, by contrast, if you have something like this, clearly, there is a straight line that does rather better than y bar. Yes? But y bar gives us a bit of a baseline. Because what we're saying is that we're interested in explaining the amount of variation around y bar. How much y bar moves around. We can cut these pieces up. Look at this and say, okay, this distance, that's what we would have used before, but now we're only missing by this much. So here we have y minus y bar. Here we have y minus y hat, yes? And in addition, we can put those two together and get y hat minus y bar. question is, well, okay, how do these three things relate? It's not obvious. I mean, right now it's pretty obvious. If you add these two together, you get this one. But it gets better, because if we're going to use these as measures of variation, we're going to have to do what we did before, square all these differences. So that's the next thing. We take y hat minus y bar squared, add them all up. We take y minus y bar, y hat, and square, and add them all up. And we take y itself minus y bar squared and add them all up. Now, which ones of these have you seen before?
Y minus y bar square.
Okay,
Y minus y bar square.
this one, yes. And what did we call this?
Was the sum squares y.
Yes, either sum squared y's or sum squared t's. This, you've also seen. Y minus the predicted y is error. Yes, exactly. So this piece is just the error. So this is the sum squared error. And that leaves this piece, which is called the sum squares regression. And now, the magic. Add sum squares regression to sum squared error, you get sum squared sum. There's no reason that's obvious, should be obvious. Cranking through and showing that that's true is kind of a pain, but it is true. And that gives us an amazing tool, because if this is the total amount of variation that we want to explain, and this is the total amount of variation we can't explain, we're going to call the sum squares regression the amount of variation that we can explain. And basically, it just takes the difference between the predicted y, and so go this line, and y bar. It's a degree to which we have a non-zero slope. And so we'll rewrite that. And now we're going to divide by a number, and it's going to be the same number we have on the left. If we divide the number by itself, what do we get? When we divide 10 by 10, we get 1. Very good. So we can rewrite and say that this thing yes? And now we're going to give that a name. This is going to be little r squared. And if this is, so this is 100%, this is the percentage of the variation we can't explain. What's left over is the percentage of variation we can. So this is a number that varies between 0 and 1, or 0% and 100%. And if you get, 5%, that's usually not great. If you get 95%, that's almost always fantastic. But it varies by the field you're in. If you're in physics and you get less than 99%, you got a problem. In certain financial studies, if you get 4%, you have a great study. Typically, in business, anywhere between 30% and 60% is really good. But it's different in HR, marketing, finance, and all these particular types of studies have different benchmarks. And actually, because this is a question of how much we're explaining, it's not the first question we want to ask, but it's sort of easier to talk about. The real question we want to ask is a formal hypothesis test. If we look at these two things, in this case it seems like we can explain something. In this case it doesn't. But if we consider the population line, if x has absolutely no impact on y, what must be true about one of the parameters?
Constant. Constant.
Yes, but we can be more precise. Constantly equal to,
0.
and which one? Exactly. Beta 1 has to be 0 in order for x to take on any value without having any impact on the expected value of y. Everyone see that? That's really crucial. If you don't see that, you're kind of SOL when it comes to the entire hypothesis testing section for regression. So that is the null hypothesis that we want to test. And it's so standard that most statistical software packages do so automatically. Okay. If that's the null, what's the alternative?
Not equal to.
Okay. And you'll be gratified to know, I hope, that you've already seen the machinery to do this. It uses a t-distribution, but with n minus 2 degrees of freedom. Any intuition as to why we lose 2 degrees of freedom? Exactly. There are 2 parameters that we've estimated, so we've lost 2 degrees of freedom. So that's really all there is to it. Questions before we actually execute this plan? First thing is to write down the equation. Once you get to this stage, you have to be able to write down y hat is equal to, and so on. What is y hat equal to? Evan?
2.2 minus 1.5 is.
Exactly. Are there any questions on this? Typically on the final, this is my next question, once you've calculated your coefficients, and I would guesstimate that roughly a quarter of those who've managed to get the coefficients fail to write down the equation line properly, which kind of boggles my mind, because it's really just a question of taking 2 numbers and putting them in the right place. So it's really important that you make sure you understand what's going on there. Okay. If you have this, can you tell me what y hat should be for the first observation, or how to find it?
Plug in xi, but
Very good. So we would have 22.2 minus 0.15 times 20. And that number is actually 19.21739. I'm going to round off to 19.22. And once we have this, we also need our error term. So now we take y is 21 minus y hat gives us 1.78 minus 0.22 minus 1.26 1.74 no minus 1.74 0.70 0.74. When you add up all those turns out to be 0, so that's kind of useless. And we squared. So 1.78 squared gives us 3.18, 0.05, 1.59, 3.02, 0.48, oops, and 0.55. And when we sum all this, we get 8.87, also known as the sum of squared errors. Right? Okay. Oh. I just erased my lovely graph. It's irritating. Okay, so we
We're,
have some points, and we have a line. Now, it turns out, okay,
Where did our error column, where did that calculation come from?
so this would be y 21 minus 19.22,
Okay. Y minus Y.
and so on.
Okay.
It turns out that the empirical rule holds for regression, and you can come up with some bands. If you want to capture 95% of the observations, you need how many standard deviations on each side? What did the empirical rule say? One standard deviation between, within one standard deviation of the mean, you should expect 68%, but close enough, 68%. Within two standard deviations, 95%. Within three standard deviations, 99.7% of the observations. So, if I ask the question, to within which precision, to within what precision could you roughly expect this model to be applied, the answer would be 2 times the standard deviation. Which is just an application of the empirical rule. That means we have to find the standard deviation of interest, right? What is it the standard deviation of? What is it that tells us how far away from this line are we going to be? What's that? Well, that's for the population. For what though? Okay, we calculate from the sample. Well, what is it that drives points away from the line?
Error.
Exactly. So we're going to calculate the standard deviation for the error term, which is the estimate for the standard deviation of epsilon, the noise term. And that is what you can apply. But in order to do that, we have to remember one thing in particular. Remember in the past when we calculated the standard deviation or calculated the sample variance, we divided the sum of squared errors by n minus 1. But more generally, we divided by the degrees of freedom. How many degrees of freedom did we just say we had here?
2.
No,
N minus
n minus 2. So, S is the square root of the sum of squared errors over n minus 2, which is square root 8.87 over 6 minus 2, or 4. And it turns out that gives us roughly 1.49. So if I ask to approximately what precision can you apply this model, what would be the answer? Okay, the units for y are the number of defects found. This is S. When I say to within what precision, we want 95% of the observations, which means you need to use the empirical rule for 2 standard deviations. 2 times S is
3.
approximately 3. So you can use this to find to within 3 defects, plus or minus 3 defects. The line speed will tell you to within plus or minus 3 defects. what you're gonna get, 95% of the time. Why is this useful? Because if somebody says, well, you predict that you're gonna sell 100,000 gallons of gas in a month, and you have a standard deviation of 5,000 gallons. Customer might ask you, well, okay, fine, but what does that really tell me? How many am I really going to sell? And you say, well, between 90 and 110,000. There's no reason for you to say between 50 and 150,000. What you can say is 19 times out of 20, or roughly that, you're going to sell between 90 and 110,000. You can use the empirical. I would argue, it took me a long time before I realized that that's actually what's going on. And that is a remarkably useful tool.
The two standard deviations are because you asked us for 95%.
Yes,
Okay.
that's right. So this distance is 2s.
Okay. Now where did the n minus 2 come from?
That's because you start out with n pieces of information, and you estimate 2 parameters, so you've lost 2 degrees of freedom. To some extent, I know that's a completely unsatisfying answer. But at this stage, that's what we're going to have to go with.
Okay.
Okay, so now we have to ask ourselves, does our model explain anything? We need to test this hypothesis. So, under the null hypothesis, beta 1 hat is centered around what? Beta 1 hat is our estimator, and it's going to be centered around the hypothesized mean of 0. The second thing we need is a standardized test statistic, which is going to be beta 1 hat minus the hypothesized mean of 0 divided by the standard error for beta 1 hat, which is not the same thing as s. And this thing is t-distributed with n minus 2 degrees of freedom. Also, however, centered around 0. But we don't need that in order to find the rejection region. What do we need in order to find the rejection region? It's alpha, yes. And if you don't know alpha, you use, what's your default value?
95.
That's your confidence level.
0.05.
105. It's a one-sided or two-sided test?
Two-sided.
Good. So we got 0.05 on each side. Oops, sorry, 0.25. And if you look up, well, okay, what is the critical value here? What should I look up to find it? And in which table? T. How many degrees of freedom?
N minus 2.
What's n here? 6. So how many degrees of freedom? 4. The heading was going to be 0.025, so that gives us a critical value of 2.776, and so our rejection region is going to be everything below minus 2.776 union 2.776 positive infinity. The only thing left over, and that we have to wave our hands vigorously for, is how in the world do we find the standard deviation of beta 1 hat, the standard error? It's analogous to the standard deviation of x bar, right? What was the relationship between the standard error s and the standard deviation s and the standard error s of x bar? Anybody remember? We took s and we divided by root n. Now we're going to do something very similar. We are going to say, and this is derivable, but we're not going to derive it. It's not root n, it's the root of the sum of squares of the x's. So we've got 1.49 over square root 1150, which it turns out is approximately 0.0439. And therefore, the standardized test statistic up here is minus 0.15 over 0.0439, or approximately 3.37, actually minus 3.37. Is that in the rejection region? It's not?
Yes, it is.
It is, it's less than minus 2.776, right? So this is in the rejection region. And we conclude that we reject the null, which means that beta 1 is different from 0, and our model explains more than nothing. That's really all we've said so far. Our model is not completely useless. The logical next question, I would argue, is, well, how much better than useless? And we've talked about how to address that issue. What's the answer? What should we look at in order to answer the question, how much of the variation in y can we account for by x?
Error term? Using the error term?
We're going to use the error term, yes, but where are we going with the error term? What particular animal are we going to find? No?
Yeah.
What's that?
Can you repeat?
Well, we're going to find something that tells us the proportion of variation in y accounted for by x. What did we call that? No? Not ring the bell? I think you're either saturated or this close to saturation. The answer is r squared, which we just talked about. So r squared, you'll recall, is 1 minus the sum squared error over sum squared total. So it's 1 minus 8.87 divided by 34, which is approximately 0.739, or 74%, roughly 74% of the variation in y, and the variation in the number of defects found, is accounted for by the line speed. That tells you something about the amount of variation that might be accounted for by variables we haven't included and should have, or just the noise term, the error term. There's always going to be some noise or error term in a regression. Okay. If we wanted to use this model to predict the number of defects found if we set the line speed to 50, would that be valid?
What is it?
50 would be here, and it would be a value for x. Would that be okay? Yes, because it's within the range for which we have data, right? It's between 20 and 60. There's nothing wrong with that. And if we did, we would find that y hat, when x is equal to 50, is equal to 22.2 minus 0.15 times 50, which is 22.2 minus 7.5, which is what? 14.70? That's our estimate. So this is how you would plug in the values for a new car or a used car that you're trying to sell or buy or whatever, or the value of a house that you're trying to. Usually you have more than one variable when you're dealing with these things, but we'll get to that next week. Let's make sure that we've already gotten to slide 5. Doing great. So this is our R-squared. One thing that I might point out, there is a relationship between the correlation coefficient and R-squared. You take the square root of R-squared and multiply by the sine of the slope, and you get the correlation coefficient back. The problem is, that's not true if you have multiple regression. That might be obvious, I suppose. But R-squared still exists and can still measure the amount of variation we're able to account for, which is a very useful tool. Okay, the assumptions that we need for epsilon, we've already assumed that it's normally distributed with a mean of 0 and a fixed standard deviation. We also have to have that the noise terms are independent. So, for instance, if you're trying to figure out how people liked, Delta's new seating or something on a plane, you can't just stand and ask every person that comes off the plane. You'd have to at least space your questions, because you might typically get couples or families or people from the same company, and they might have very similar answers. So you need independent samples, which shouldn't be terribly shocking. This has to do with this t-test. We also have what's called an f-test, which is not terribly interesting until we get to multiple regression. F-tests don't have this distribution. They basically look at whether or not the amount explained is valuable, the additional amount explained. Alright, so this is again looking at the both S and the standard deviation of theta 1/2. I think that's it. Let's see. Yeah, suppose I could have gone back and forth between the slides a little bit more. The problem is that it's a very picky topic when we first encounter it. Next week, when we do the same thing, we're not going to do this level of nitpickiness. We're going to instead use a computer to give us coefficients, and we're going to talk about how these things work together. But we're still going to find estimates for y. Error, we're going to look at sum squared errors. We're going to calculate and interpret S. We're going to do hypothesis tests, various types, and we're going to calculate R squared. So if you really get this example, get this univariate regression, you're, I would argue, between 80 and 90% of the way to understanding multiple regression. So it is I would argue it is a useful tool. Are there any questions? Okay.
Understand the calculations in R squared. I don't necessarily understand what that's telling us and why.
Okay. There are two ways to address that question. Either cranking through the math, which would take too long, or just talking about it. Does it make sense that the sum of squared errors is the amount, is sort of a measure of how much we can't explain, like a measure of how badly our line fits the data? No?
I'm not comfortable with it.
Okay. Does it make sense that we would like the sum squared errors to be 0, or that it is 0 when all the points are on the line?
Yes.
Okay. So, to some extent, the sum of squared errors is related to the fact that the points are off the line. Right? And if the data points are just spread tremendously, that's going to give you a much larger sum of squared errors than otherwise. Alright. The total sum of squares just looks at how much the data points are off a horizontal line, y bar. So you can't possibly get a larger sum of squared errors when you have the option of moving the line, right?
Okay.
Well, because you could have always chosen this flat line, yes? Okay, so the sum of squares total, the variation around y, has to be larger than the sum of squared errors. What we're saying is that by tilting the line, we're reducing the variation around y, around the line. Can you picture that in your mind's eye? Okay, how much more? Well, it's the amount we lost. It's the difference between the total variation around y, around the mean, and the total variation of the error, which is sum of squared errors. That is what we say we explain, or accounted for. When we calculate that ratio, we argue that that's the proportion we have accounted But you're right, to some extent, it's a definitional issue. I mean, have we accounted for it? It's not, nobody's claiming that we have causation here. We have correlation, but it's not necessarily causation, so explained is too strong, really. Accounted for is at least vaguely right. We'll work
A
on it.
little more
So-
comfortable with that.
If you have data that looks like there's no relationship at all, with a computer program, you can just simply move the line so the sum squared errors is smaller, and that would present the relationship.
No, you'd have to invent data in order to come up with any reasonable line. Unless you're just drawing a line, and in that case, you're never going to come up with, you're never gonna pass this next test. And this is just a way to keep people honest, right? When you're doing a formal hypothesis test, you're never gonna be able to fail to reject the null if your model is useless. Okay, if you move your line just willy-nilly, you can come up with a new sum of squared errors, sure. But it's gonna be a larger sum of squared errors than you would have gotten by calculating it using ordinary least squares. And so you're never going to be able to reject the null hypothesis that your model is useless. But look at that more next time as well. Trish?
How did you, I think you explained error I, 21 minus 19.22. How did you get that? Which equation did you use?
This, 20, this part, 21 minus 19.22, step by definition. Error, E, is equal to y minus y hat. Remember? Other questions? Okay, here's my suggestion. Either close your eyes for a minute or two, or you're welcome to use this opportunity to make a break for it. But I'm going to go over, just quickly show you how to do this in Excel, if you have any interest in it, or if you want to do this in the project. That's the plan, but I won't do anything for a minute or two if you prefer to leave.